Hey, welcome to lesson 4.7, independent and dependent events. So if we take a look, we've got a multiplication law. So there's two different multiplication laws, one for dependent events and one for independent events. So if an event is independent, the first event does not affect the second event. Okay? So they are independent if it does not affect the second outcome. However, we say they are dependent if they affect the second outcome. Okay? So, what is the biggest thing for dependent events? Well, it's the way we write the equation. But it's not just the way we write the equation. One of them is, and you're going to notice this big one, is the totals differ. And that's going to matter coming up. So let's take a look at an example. So if we take a look at a couple examples, so if we talk about something not affecting something else, that's an independent event. We have our first example here, our keyword, and this is a keyword that you will see for independent events, and that's replaced. So independent events match replaced, okay? Now, if I've got a deck of cards, and we always say there are 52 cards in the deck. Okay, so I've got 52 total cards in a deck. That's why they call it a standard deck of cards. So it says we draw one out, then we put it back. The minute we put it back, we're not changing the total amount of cards. The total amount of cards is still 52. If we're not changing the totals, then that means that there is nothing different in terms of my probabilities. So, my first card is a heart. Well, I have 13 hearts out of 52. If I put it back and I take out another card, there's still 13 in 52 chance that I'm going to get a heart, which is 1 in 4. So I still have a 1 in 4 chance that I can pull out a heart. So, my first event did not affect the second event. So if we take a look, the bottom number and the top number did not change. But if I take a look at my second example, I didn't put my card back. I'm not replacing it. And that's a huge keyword here for not replace, matching dependent events. So you're going to pick a card out. You're going to check and see if it's a heart. Well, we just said that there are 13 in 52 hearts. That means a 1 in 4 shot of picking a heart out. But if I don't put that card back, I now only have 51 cards. And if that first card was a heart, how many cards are gone, or how many hearts are gone? There's now one less heart to pick from. So I don't have 13 hearts anymore, I have 12 hearts. And I don't have 52 cards anymore, I have 51. So that's what I mean by the totals are different. We have less cards to choose from, so it affects the probability. So 12 and 51 is a very, very different probability than 1 and 4. Okay? So when totals reduce, that's when we notice that it's going to be a dependent event. Now, do both totals have to reduce? No, only one of them has to reduce to be considered a dependent event. Let's take a look at the next ones. So not replace, not putting something back. This affects the totals. Okay? It affects the total amounts. And whenever the total amounts are affected, that's when we have a dependent event. So, let's take a look at this first experiment. We got a die and a coin. If I roll a 2, does it affect me tossing a coin at all? Does rolling a die affect a coin? Never. So it will always be independent. Okay? Me flipping a coin does not affect me rolling a die. Okay? The next, I'm going to draw 2 cards. Keyword, without replacement, so you're not putting it back. The minute you see that not replacement, that is an indication, dependent events all day long. So D for dependent. Okay, so not putting it back, that changes your total amounts. So if you're changing your total amounts, it's a dependent event. C, you've got a spinner. Yeah, you got a fidget spinner here. The first event, the color is red, and the second event, the color is red. So you're spin red once, spin red again. Well, even though it's the same color, does you flicking that spinner and flicking it a second time affect each other? No, they don't affect each other. They are independent. Okay, so the spinner will not affect each other. The only time it's going to affect it is if the total is changed. Okay, so if the total amount is changed somehow. All right, let's take a look at another example. So we're going to look more specifically at dependent events, because independent events we've been dealing with already. Just take your totals and multiply. But the minute we put a condition in there, that's our conditional probability. So let's take an example here. So first of all, though, it tells us dependent events create a scenario where the probability of an event can change depending on what's previously happened. Okay, and that is your conditional probability. And again, that means that something has changed the total amount, because you will always get a conditional probability when the total amounts are changed. So we read it as this: PB/A, and that slash is not a forward slash or a backward slash, it's a straight up and down. And that straight up and down means after it has already occurred. So, given that blank has already occurred, so whatever the actual outcome. So, it's B after A happened, is that how we would read that? So the probability of B after A already happened, or the probability of B after A occurred. Okay, officially. So, and this guy, with the tick there, with the prime tick right here, we would just say the probability that B occurs given that A has not occurred. Okay? All right, let's take a look at these ones. So you got a card. You're going to draw one, then you're going to draw two. And it's not put back. That's our key. It's not put back. So the first event is red. The second event is a 9. Well, first of all, we need to know what is the probability of picking a red 9. Red and 9. Well, how many red cards are there? 26. But how many are actually only red 9s? There's 2 red 9s. You have a red diamond, okay, a red 9 of diamonds, and a red 9 of hearts. So there are 2 in 52, which reduces to 1 in 26. Okay, so that's what you're combined, okay? That's our and. That's the probability of a red 9 coming up. Now, if we look at our probability, we have a equation, and it's this. Probability of A and B is equal to the probability of A multiplying by the probability of B. That's if it's an independent event. We're dealing with dependent events. So that means that they're changing this part, the second part. Now the second part means that we're changing it to B after A occurred or B after A didn't occur. So that's what we're working on. We're changing them to these right here. So we set it up into a little tree diagram here. So we have A and B on top. And on the bottom, we've got A. And here we have B/A. B after A occurred. So if I want B after A occurred, and this is the same way I would set up an equation like I had speed, distance, and time. So distance is rate of speed times time. Same idea with using this kind of triangle. You cover up what you're looking for. If I'm looking for speed, I'd cover up R, rate of speed, distance divided by time. Same idea over here, okay? The bottom two are multiplied. That's if I'm looking for the top one. You cover it up. So A and B, you've multiplied both of those. So right now, they want B after A occurs. So they want this part of my section. So they're looking for this one. So if I cover that one up, I get A and B dividing by A. So that's what we put in our equation first. So we got to write the equation down, and then we got to fill it in. So we need to put down probability of A and B dividing by probability of A. Now here's a good way to remember it. Whenever it's written B slash A, so B after A occurred, whatever letter is written second is the one that's on the bottom to divide by. Okay? Because if I was asking for B, if I change this letter here to a B, these two letters switch. It'd be A after B occurred. Okay, so your triangle would switch depending on if you're looking for A or B. Now, up here, A and B. We already said A and B is 1 in 26. So I have a 1 in 26 shot of finding A and B. Okay. Dividing it by the probability of A. Well, what is the probability of A? A means red cards. What's the probability of picking a red card out of the deck? Half are red, right? So we would say half, because half are red, half are black. So you're going to divide it by 0.5. Well, if you math frac that, you're going to get 1 in 13, which is 0.077. Okay, that's rounded. So you get a 1 in 13 chance of the probability of B after A occurred showing up. Okay? Now, what does it mean by B after A occurred? Well, that means you're picking a heart after you already picked a red one. Okay? Because the first one's saying you're picking red. B is saying you're picking a 9. Okay? So what did we just find out? We picked picking a 9 after we already picked a red card. It's going to come up 1 in 13 times. Okay? That's what we just figured out. Now we're going to figure out the next one. So, B after everything that's not A. Well, after everything that's not A, what would they mean by that? Right, exactly, because A is red. So everything that's not red is black. So that means we want the probability of B, a 9, after we picked all the black ones. Okay? So we're going to have the probability of A and B divided by the probability of A prime. Okay? Because remember, it's always the guy on the right who's written second is the one you divide by. Okay? So the guy that's written second is who you're dividing by. So we said A and B is how big? Probability A and B is 1 in 26. So we have 1 in 26 dividing by, and now what's everything that's not red? Half. Good. Is the answer going to change? No, it's going to be 1 in 13. Now, how would it change if I did this? If I said, if I switched those around and said A after B occurred. So I want to switch letter A around. So we're going to do another example. This is going to be example C. And example C is going to be identical to A, but I'm switching A and B around. Okay? So I'm just going to write it down here, just so you guys can see. Okay? So we're making a letter C. Here's our letter C. I want the probability of A after B occurred. Well, that's going to be probability of A and B divided by which letter is written second? B. So B's in the bottom. Probability of B. Okay. And we said A and B is how big? 1 in 26. Well, what's the probability of B? A 9. How many 9s are in the deck? 4 in how many? 52. So 4 and 52 are 9s, which gives us 1 in 13 are going to be 1 in 13 are 9s, okay, because 4 and 52. So we reduced it. Now, if we divide those, we're going to get 0.5. So we're going to get the probability of A after B occurred. So basically getting a red card after I pick a 9, that's going to be half, 50-50 shot. Okay? That's what we just figured out. All right. Let's take a look at number 2. Now, number 2 is going to be very similar to what we just did. Okay, I'll just give you a minute to write that down. Okay, carrying on. This here, there's 7 black candies in a bowl of 40. Determine the probability of getting a black and then another black one after you eat the first candy. So, how do I know this is a dependent event? Good, because we're not replacing it. We took the total different, right? The total is different because I ate one. I took one out. Didn't put it back. So that means I want the probability of black times the probability of black after I ate a black. Okay, that B/B, that's what that means. It's the probability of pulling a black one and eating it after you ate the first black one. Well, there are 7 in 40 that are black. I ate a black one. How many are left? 6 in 39. That's going to give us 42 in 1560, which is 7 in 260. So that's the probability of picking 2 black ones, one after another, and eating them both. So this again is a conditional event. Now we're going to talk about the difference between whether something's mutually exclusive versus independent or not. Okay? So now we're going to be going back to the 4 formulas. So the 2 formulas for OR, the union, A plus B, or A plus B subtract the overlap. Now we've got A times B, or A times B after the B occurred. So let's take a look here. So it is important to note that these are 2 separate concepts. Mutually exclusive deals with you doing one event only. So mutual exclusivity you're doing and you're checking one item, you're checking one thing only, and you're comparing it. If you are doing a independent versus dependent, that means you've got more than one event happening. Okay, and you're comparing to see whether it changes the total or not. So, mutually exclusive events are ones that cannot occur at the exact same time. Independent events don't affect the probability of the other guy happening. Dependent events do. So, this is the way we check them. And again, we always check them with our probability formulas. So we're just going to jump right into our formulas. So example 1, I've got probability of A is 1/3, B is 2/5, and it's giving me the OR is 3/5. Now, the reason they're giving me an OR is because if I check all my formulas, I've got this. A or B is probability of A plus probability of B. Okay, there's my first one. So I've got this formula. And then I've got the same one where they have to subtract the overlap, minus A and B. Okay, that's your subtracting overlap part. Then we've got the AND ones, where we've got probability of A and B. That's your independent. That's just A times B, probability of B. Then we've got the dependent ones, A and B. Probability of A, probability of B after A occurred. So this part tells us it's dependent. So that's the difference. And this part here tells us it's non-mutually exclusive. So the way the formulas go is this. We've got mutually exclusive, non-mutually exclusive, independent, dependent. And we have to decide which ones to use. So how do we know which ones to use? It depends on the information given. So I take a look at my question, and they gave me an OR. So I need to check out my first or question to see if the left side equals the right side. That's what we're trying to check on all of them. We're trying to see, does the left side of the equation equal the right side? That's what we're checking. Okay? And if they do, then that means it's either mutually exclusive or independent, depending on which equation you're checking. So I'm going to check the mutually exclusive one. So probability of A, let's see, or B. Let's just get that guy up here. All right, so I'm using that one right here. It says the or is 3 over 5. It says A is 1/3 and B is 2/5. So if the left side equals the right side, we need to be able to do common denominators. Okay? So common denominators, because we're adding and subtracting. Whenever you're adding and subtracting, you need common denominators. So in this case, it's going to be 15. So we would take our numbers and change them out of 15. Okay, so I've changed my bottoms to 15 down here. Now I'm going to change my top. So this guy times by 3, I'm going to times my top by 3 to get 9. Over here I multiply by 5, multiply my top by 5, multiply by 3, I get a 6. 9 and 15 is not equal to 11 and 15. So I got my left side is not equal to my right side. So does that mean they're mutually exclusive? No, it means they're non. The reason they're non is because there's an overlap. What would I have to subtract from 11 to become 9? We have to figure it out. 2. So the number you subtract here, and this is how it will always work. If you need to subtract a number in order to make the left side equal the right side, this is now your overlap number, which is the A and B number. So now we've figured out the A and B number. We know A and B happening is 2 and 15. Okay? Now, the reason we figured that out is because left side didn't equal the right side here. If left side equaled the right side, there'd be no overlap. That means they'd be mutually exclusive, no touchy-touchy. But these guys are overlapping. Okay? So that means they're touching all day long. So, when we go up and answer this question, is it mutually exclusive? No, because there's an overlap. Now we're going to check the independence. So when I check independence, I'm checking my first red equation here with my multiply. I figured out the and. The and is right here. Positive 2 over 15. So I'm going to put my numbers up into the equation right up here. So my and is 2 over 15. Probability of A, 1 over 3. Probability of B, 2 over 5. When I multiply the right-hand side, multiply tops, multiply bottoms, I get 2 and 15 equals 2 and 15. Here, my left side equals my right side. So that tells me, yes, they're independent. Okay? So over here, they were not mutually exclusive because there was an overlap, but they were independent. So this is where people get confused. How can something be independent, but yet have an overlap? Well, that's like saying the example like my spinner and my die we talked about earlier. If I've got a spinner with the numbers 1, 2, and 3, and my die also has the numbers 1, 2, and 3, they're two different objects. They're not going to affect each other. So they're independent of one another. But do they have overlapping outcomes? Yes, they do. The numbers 1, 2, and 3. Okay? So that's how something can be independent and yet have an overlap. Okay? So those guys don't affect each other, but yet they can have an overlap. Okay? All right. We're going to do the exact same thing with number 2 here. Okay? And again, we've got to check our two basic equations. We're checking the top one, the or, and then we check the very first red one, which is the and. Okay? So these are the two we check automatically. We check the or, which is mutually exclusive, and we check the and, which is independent. Okay? Those are the two we're checking. I'm going to erase everything else. Let's get started. So, we're going to do this question now. I'll just erase it all. Okay. Moving on. So this question right here. Found that 4/5 like chips and pop. So we have chips and pop. And it was also found that 9/20 like both. So it says if we've got both, we've got an overlap already. So are they mutually exclusive and independent? Well, if we have an overlap, can it be mutually exclusive? No. So these guys are non-mutually exclusive, so they're not. Why? Because we have an overlap. We have a both. The minute we have a both, there's not mutually exclusive. So we figured that part out already. Now we need to do the independent part. So independent means probability of A times probability of B is going to give us the probability of A and B. That's what we're told. So if the probability of A is chips and B is pop, we have 4/5 liking chips, 3 out of 5 liking pop, and we have 9/20 that like chips and pop. Well, if I multiply these, I'm going to get 12 in 25, which is not equal to 9 in 20. So that means it is dependent. That's what it tells us. Okay? So it's a dependent situation because the left side did not equal the right side. Any questions there? Okay, you've got a couple minutes. We want probability of blue and yellow, which is probability of blue times probability of yellow. So my blue, 5 and 11. My yellow, I got 6, but I didn't put that blue hat back. So that means I've only got 10 to choose from. So that's going to give me 30 in 110, which gives me 3 in 11. Okay? So remember, if you're not putting it back, it changes the total. Now, how do we know that we're using and? You have to read the question, and it's what they're joining them by. Okay? The next one says we're drawing 2 cards without replacement. So we're drawing one, keeping it, and then drawing another one. So pick and pick. So that means we want red and red. Well, red and red. So what is my probability of red? 26 and 52. All right. You didn't put one of those red cards back. How many do you have left? 25 and 51. Good. So now you're going to multiply your top by top. 650. Bottom times bottom. 2652. And you math frac that. That's going to give you 25 and 102. Okay? Well, let's take a look at the next one. You want to put neither card as red. Well, is that the same thing as saying I want to pick black and black? Would that have a total different other than the red and red? No, it would be the same as A. Okay, same as A because there's an equal amount of black and red cards. If there was a different amount of black and red cards, the answers would be different. Yes.
So why did you subtract why did the total change
On the first one?
on the first and the second, like we have the multiplication and then the total change? Why did that one not?
Okay, and it's because it says that we didn't put it back without replacement. So I picked my first red card, but I didn't put it back, so that means there's one less red card. There's one less card in that. Okay, so we have to make sure we remember that. Okay, letter C. Letter C is quite a bit different. So C and D, watch carefully. With letter C, we want probability of a king and a 5 in that order. Order is important. So, kings. How many kings? 4 out of 52. How many 5s? 4, but I already put my king out. How many are left for cards? 51, because there was 52 to choose from, but I picked one card out. Yeah, you don't subtract 4. That's the myth. That's where a lot of kids are going to get that wrong. You don't subtract those 4. You just subtract one card that you pull out. Okay, and that's a common problem. So make sure you just subtract one total for the bottom here. Now, the tops didn't change, though, because 5s and kings are different. That's why. So now we want them in that order, 16 in 2652, which is going to reduce to 4 in 663. Now, letter D says you want to pick a king and a 5, but does it tell you the order? No. When it doesn't tell you the order, you have to consider both orders. So you have to consider the order king and 5, and then you got to consider the order 5 and king. So you consider both orders and then you add them. Well, they're going to be identical. So basically you take the answer and multiply it by 2. Because this answer is going to give you 4 in 663. This answer is going to give you 4 in 663. Which means we're going to get a total of 8 in 663. Okay? So if you just doubled your top number over here on letter C, that's all you had to do. Okay? Now again, this is non-order specific. Order does matter and it will play a part. All right, let's take a look at our last few examples here. So, conditional probability using formulas. Okay. These are the ones where we've got to go through our triangle formulas again. So, this is where we have A and B on top. Over here, we're going to have A, and then B after A occurred. Now again, remember, if B was on the left, the A and B on the right would switch places. So, if I wanted B after A occurred, well, I cover that part up, and then I know what I'm dividing. I take and I divide it by A. So, I'm going to have probability of A and B divided by probability of B. Nope, sorry, A. Probability of A. Okay, well it's telling us the and is 1 over 4. So I'm going to have 1/4 divided by 1/2. And that's going to give us 1/2, 0.5. So B after A occurred is 0.5. Now we're going to look at the next one. What about A after B occurred? What if I changed up the A and the B? Well, all that matters is on the bottom. We're going to notice that right here, we change the letter. It depends on who we divide by now. Since they wanted A first, then B, the number on the bottom changes in my actual equation there. So I'm going to have probability of A and B dividing by probability of B this case. So that's going to give me 1/4 dividing by 1/3, which is going to give me 0.75. And then we'll do letter C. Letter C wants the OR. If it wants OR, we need to add and then subtract the and. So, we are taking these guys and we're going to add them and then we're going to subtract the and. That's the whole thing we're doing there. So, since we're adding and subtracting, we need to do a common denominator. We have a 2, a 3, and a 4 on the bottom. A 2, a 3, and a 4 will give us a 12 for a common denominator. So our common denominator, this guy is going to become 6 out of 12 plus 4 out of 12 minus 3 out of 12. And that's going to give us 7 out of 12. And that's the OR for letter C. Letter D. Independent. If they're independent, that means the probability of A times B should give me the probability of what they tell me the and is. So we need to take a look and do that. So we need to take A times B, so 1/2 times 1/3, and that's going to give me 1/6. Is 1/6 equal to my and 1/4? It is not equal to 1/4. So if it's not equal, it is not independent, it's dependent. Okay? Because we had to come up with the answer of 1/4. Did it equal 1/4? No, it did not equal 1/4. Okay, so the left side did not equal the right side. That's why it's a dependent event. We're going to do the same thing with number 2 and number 3. So with number 2, they gave us the and they gave us A. They want us to find B after A occurred. So, probability of B after A already occurred is equal to probability of A and B divided by probability of A. And that's going to give us 0.5 dividing by, I used the wrong number there, 0.725. 725 over 0.78. And that's going to give us 0.9295. So 9295 is what we get. The next one, blonde and tall. Well, if being blonde and tall is 0.5, tall after already being blonde is 0.68. We want the probability of blonde. Well, probability of blonde is going to be the probability of blonde and tall divided by probability of tall after blonde occurred. Now we're just dividing. So we've got 0.5 dividing by 0.68. And when we do the dividing, that's going to give us 0.7353. All right. Now we got the computer manufacturer. Same idea. Okay, in the computer manufacturing, it says that a box of 100 chips, 3 are guaranteed to be defective. Determine the probability that Jocelyn's going to draw 2 defective chips, one right after the other, without putting them back. So she's not putting those defective chips back. So that's right here. So they're showing us the equation to use. So we've got 3 and 100 are defective. So the first chip she has, she has a 3 in 100 shot of grabbing a defective chip. If she pulls one out and doesn't put it back, how many chips are defective left? If 3 were to start with, how many are left? 2. And if she pulled 1 out of that batch of 100, how many are left? 99. So that's going to be 6 in 9900. Which is a 1 in 1650 chance of pulling out 2 defective chips, one right after the other. So the next couple questions are for you to do for your homework. We will pick this up tomorrow. Okay, you've got a couple minutes to take a look at these. Let's see how you did, okay? So, passing math and English. Most of you, as I walked around, were doing the probability charts. So the pass versus the fail. So math and English. So 0.7 and 0.3, 0.9 and 0.1. So passing math and English would be 0.7 times 0.9 to give us 0.63. Math or English means I'm going to add the numbers, which is going to give me 1.6. So or meaning adding. Passing math, but not English. So now you're going to multiply those two. So 0.7 times 0.1 to give you 0.07. Further down, if we took a look, and if you actually drew a Venn diagram of what was described here, we have prime numbers, and then we have the odd numbers. Your prime numbers and odd numbers from 1 to 10. So if you were to split it up like that in a Venn diagram, now all you need to know is H is your prime number. So we want probability of prime is 4 in 10, which is 2 in 5, which is 0.4. Probability of an odd number, 5 in 10, which is half, so 0.5. And so how many are in the overlap? So this is the overlap section right here. So we're going to see 3 in 10, which is 0.3. The or just means add up how many numbers are in each section. So there would be 6 in 10, which gives us 3 in 5, which is 0.6. Now, this one right here, that one is asking us probability of prime after odd has already occurred. So that's going to be probability of prime and odd divided by the probability of odd. So that's going to give us 0.3 divided by 0.5 to give us a total of 0.6. Check your work. Make sure you did it right. Okay, our last section is we can set up those same types of charts like we just did. Like, for example, with the pass and the fail. Okay, success and failure for each. I could do the exact same thing here for this next example, and I could set it up as good economy, bad economy. So we would technically probably set it up like this. Good economy, bad economy, sales of 10 million, and here is not 10 million. So you could set it up that way. So if we set it up that way, we have 0.34, and this will be 0.66, and then we'd have 0.54 and 0.46. So that's how we could set it up if we set it up that way. If not, we would set it up this way. So we set up good economy to bad economy. So we have the sales projection, which is what we've got here, our first spoke, so our sales projection, and then we compare our good economy to bad economy. So running it out as a diagram for a tree chart, we would continue it like this. So again, it shows us which sections we would be multiplying. So here I'm going to take 0.34 and I'm going to multiply it by 0.46. And over here I'm going to take 0.66 and multiply it by 0.54 and 0.66 times 0.46. And that's going to give us a total of, for our first one here, 0.1564. The next one, 0.3564, and the last one, 0.3036. So it says determine the probability that the expected sales will be $10 million. So, and a good economy. So we wanted this way, expected sales 10 million, good economy versus bad economy, it could be this or this. So if we said or, we would add both of those totals. So, determine the probability they will be that. Well, it's either going to be this or this. So I would have 0.1836 and I would add it to 0.1564 for a total of 0.34. Okay? Let's take a look at the next example. These are ones I'm going to give you a couple minutes for. Push pause now, play when you're ready. Okay, you've got a couple minutes to look at them. Hopefully you drew your little charts and pass, fail. And we've got math and English, 0.8 and 0.2, 0.9 and 0.1. So how did we get that? Well, these are the odds against and odds in favor. So what we did was we took those odds in favor and odds against, and I converted them to probabilities. So that was the very first step that you should have done. Now, the very first one, we should get 0.72, 0.08, 1 minus neither, which could be 0.98. In probabilities, passing, 4 out of 5 is 0.8. 9 out of 10 is 0.9. That's how I got the 0.8 and the 0.9. All right, so probability formulas. For the first one, passing math and English is going to be 0.8 times 0.7 to give us 0.72. Math or English, or sorry, math, not English, probability of math and non-English, 0.8 times 0.1 to give us 0.08. Triple I, probability of math or English, that's going to be the probability of math plus probability of English minus both, which is going to give us 0.98. Okay, let's take a look and see how they filled out the tree diagram down here. Same idea. This would be 0.1, 0.9, 0.1, and this is 0.2 here. So this would be passing math and not English. Passing not math and English. Passing not math and not English. So 0.8 times 0.1 to give us 0.08. 0.2 times 0.9 to give us 0.18. 0.2 times 0.1 to give us 0.02. So those are the probabilities you should have found. So as you can see, you can draw them in a tree chart, or you can draw them just in a probability chart. The last question here, field hockey game. This one you had to set up completely by yourself. As I was going around, most of you did quite well at this. So let's take a look. We want probability 1 goal or no goals. Well, first of all, we want probability of a goal, and that is 1/8. Well, probability of no goal would be 7 out of 8. So this is 0.125. This is 0.875. So again, we want to score a goal and no goal. So score a goal again. 1/8 over 7/8. 1/8 over 7/8. So probability of a goal and a goal is 1/8 times 1/8 is 1 in 64, which is 0.015625. And we want probability of a goal and no goal. 1/8 times 7/8 equals 7 in 64, which is 0.109375. And the same thing here, probability of no goal and a goal, same as above, 1/8 times 7/8 to give you 7 in 64, 0.109375. And probability of no goal, no goal. No goal and no goal. 7 over 8 times 7 over 8 is 49 and 64, which is 0.765625. So that's a lot of probabilities there. So now we're going to go and answer our questions. A, probability of 2 goals, 1 in 64. Probability of 1 goal, well, they didn't say if they scored first or second, so you take your 7 and 64 and add it to 7 and 64. You have to take both of those and add them together. So you're going to get 14 and 64, 4 points, which is 0.21875, at least 1 goal. So that means 1 minus no scoring, 1 minus not scoring is what it is. Well, and not scoring is 49 and 64. So that means it's going to be 15 in 64, which is 0.234375. And probability of no goals, 49 in 64, which is 0.765625. Now, if we take a look at these two are complements. As you notice, I took on letter C 1 minus not scoring, so no goal, no goal, and no goal, which was this. So if I took 1 minus the 49 and 64, that's where I got my 15 and 64. So if I added this probability right here to this probability right here, I'm going to get 1.0. This concludes our last lesson of our Unit 4, Set Theory and Probability.